Okay, so now I'm going to move on to talking about test benches, because once you've gone through the pain of building up that, again, using the supplemental walkthrough, we'll give you as much or more information as I've given you in this lecture. You need to move on to the test bench section. Now, the test benches are all built up in pretty consistent ways, and I'm going to talk some about how you do that. So the first thing that you're going to do in a test bench is, sorry, let me find my notes, make sure I don't forget anything. You always start just by declaring some entity. We'll just call it TB for test bench. And then you're going to just say is, and then end it. So that just sits at the top of the test bench. It's just the declaration. But then we need some architecture of it. Right? So we're going to have some architecture that we're going to build here. Just inside of architecture, after you say this, this is where you're going to declare any of your signals. And it's also where you're going to declare any of your components. Now, signals are how things are going to be wired together, and components are going to be, well, in this case, it's going to be your receiver. It's going to be your UUT, is what we call it, unit under test. The way we do this specifically, so this is kind of the pseudocode, right, is we say component. It's going to be some UART RX is what I called mine. Your may be different. Mine's UART RX2, technically, because I've designed multiple of these. And then you're going to set up your ports, and you're going to have, right, it's going to be like a clock, which is an input of type standard logic. Semicolon at the end, new one. I'm going to have a reset, right? This is the declarations that we were given as part of the lab, so we need to make sure these exist. This is also an input of type standard logic. Then we're going to have S data, P data, ready, and then we can ... end component. Okay, so this has created the component inside of the architecture. Signals, some signals that I might need, just a quick example, I would say signal. I need a clock, so I'm going to call it TB clock. Because it's not the clock that's internal to that signal, it's a signal to the test bench. And this signal is going to be floating around and is going to plug into that port. But I need to create it first. And it is standard logic, right? Because it needs to match type. If I'm plugging standard logic into something else, it would be problematic, so I've got to match them. And I'm going to initialize it using a colon equals. Ticks means it's just a bit, and it's 0, right? Similarly, I would do signal for reset, a signal for S data, a signal for ready, and a signal for P data. The ready seems to be something that gets people confused, right? And I've explained this in lab, but hopefully this will help for anybody that missed it. So your receiver is going to have some register of data where it's going to save things, right? And it's pumping data into this register. When it's full, there's going to be some external circuitry that is waiting for this, but it needs to know when. So this is going to output a ready signal that you could treat almost like a clock to a series of flip-flops that just say, on the rising edge of ready, clock whatever is on the inputs into my outputs so that it's stored, right? And then this we can treat as memory that can be accessed by other more complicated circuits. While this is still being accessed, then we can start reading in more data without corrupting the data we still need to work on. So we read in, start working on it. While we're working on it, we can keep reading in. That's why we want this ready signal to say, hey, take me out of here. Or it can be used rather than the memory. It could be say, hey, do stuff with it. Right? It's just to let it know that this buffer is full. It's done accepting a complete command. Go. Okay, so back. So we've created a signal for clock. We're going to do reset and so on and so forth. Now you can also declare constants by saying constant. This is going to be we'll call it bit period because I use it in my code. That bit period is going to be of type time, which seems weird to people, but a time type exists. And I'm going to initialize it to 8,681 nanoseconds. Now, how you get this number, you can puzzle out. But if you use the same baud rate and clock speed as me, you'll get this number. Otherwise, this number could be different because your bit period might be different. Now, there's another cool thing that we can do also just under this architecture that is called procedures. Now, I think I've given you the procedure I have in the example, but procedures are like processes, but explicitly for test benches. So I have one procedure called TX bits. It takes some inputs and takes an input, has an output, and does a bunch of stuff. You can read through it. But the whole point of that is this is how I'm going to simulate the transmitter. That's what this procedure is doing. It can simulate a transmitter. Once I've done that, once I have the procedure, after all of this, now I can do begin. Now notice this begin actually ties all the way back to the architecture. So this is actually architecture begin, but this is declarations going on of signals, components, ports, and procedures. Now that I have these signals inside the begin, I can start making assignments. Like I can say the TX serial is 0, right? And then I can tell it to wait for bit period. Right? Wait for bit period. Now, wait for, this is time, will not synthesize, but works great in test benches. Now, this is where we have this thing called loops, which you're familiar with. I'm starting from other programmings. For I in 0 to 7 loop, right? I use II rather than just I because all of my loops I use double variables, II, JJ, KK, to differentiate them from I, right? Or the imaginary number, or J, the engineer's imaginary number. I don't like even KK, which isn't really used for anything else. I use KK. I do not like single variables for loops. I avoid it like crazy. So this TX serial then that I've set as 0, it probably makes more sense to set that as 1 to start out. Otherwise you might end up with an issue in your state machine and needing to reset. But you can do, so for II, TX serial, sorry, I'm writing the procedure out in this. This is all going in the procedure. Lost track. I should restart the video, but I'm not going to. Okay. Ignore all of that. That's what's going in the procedure. It's been given. So inside the begin is where the instantiation happens. What that means is I'm going to say Rx. This is just the name of an instance of UART RX, and I said this one was UART RX2 because it's the second one I designed. Now, something I can also do is map the ports. Port map. There's two ways to do this. Is you can either put them all in order, so it would be test bench clock, because TB clock needs to be mapped to clock, and then it would be TB reset to reset. Or I can go through systematically and say clock is mapped to TB clock, and reset is mapped to TB reset, and so on and so forth. So that's explicitly mapping them together, or you can just put them in order, TB clock, TB reset, and so on and so forth, separated by commas. Either is fine. The system actually really hates using the ordered ones. It very much prefers this because, rightfully so, it believes this is harder to screw up the wire connections, because this is telling it how to connect things together. Okay, so after this instantiation happens, it's creating an instance of URRX called RX. I want to do something else, which is I need a clock to the system. So TB clock is going to get assigned to not TB clock after 10 nanoseconds. 10 nanoseconds is the time you need to make a 100 megahertz clock, right? And this is what this is saying is every 10 nanoseconds flip-flop back and forth, 1 0 1 0 1 0. It is important to set TB clock, to declare it like up here, to initial value, because if you have not of an unknown, it's problematic. So you need not 1 or not 0. So it needs to be declared at heart. Okay, created an instant, created a clock. Now we can do process is begin, and now we can start doing things where we can wait until the rising edge, right? So this is a wait until rather than a wait for. Wait for the rising edge of test bench clock. After that, we need to do something with that procedure that we built earlier, or well, started building and then got distracted, but it's linked, so you have it. But we need to do something with it, right? So we've waited until the rising edge of clock, so we don't start going immediately. I've actually waited a couple of them in my test bench. We can call that test bench TX bits procedure. Remember, it's procedure, not a process. And it needs an input data, something to send. So the way I'm going to do this is X and make sure I mapped that correctly. So let's go back and look at this code where I have an input. Oh, I didn't declare it explicitly in here. But this TBS data needs to tie into the serial data input. So the S data, which is the DN in my other examples. So it's standard logic. It's taking 3F. The X is saying that this is a hexadecimal hex number. So it's, right, 4 bits per each. 4 bits, 4 bits, making 8 bits. That can be serialized into S data, which is attached to the serial data input on our component. So then you can do something like wait for a couple of clock periods, wait until rising edge, wait until rising edge, wait until rising edge, right? Wait 3 clocks or something, and then transmit another bit, T bits, X apostrophe FF, right? Which would just be a bunch of 1s, and so on and so forth, and then end process. You can then use the Vivado to either look at those signals or And I will hopefully cover this a little bit in class, but they're pretty straightforward. Let's see if I can figure out where I lost it. Yes. You can use this command, assert. Then you can add some sort of Boolean expression. And then report a string. Okay, so what this does is it's going to evaluate this expression, and if you don't fail, it's going to report. So you could say, if my p data, so something like this may be a little bit wrong because I don't use these asserts as much as I should. They're actually very useful to kind of automate your testing. So it's useful to get in. So assert p data is equal to, right, so p data, and it's probably tb underscore p data as we declared since we're doing tbs data. Assert tb p data is equal to this in Boolean. So it's going to be some bits string 00111111 or whatever 3 is, right? And if it tests this equality and is true, everything's fine. Otherwise, report bad value. Like so. So this is just going to automate the testing a little bit. You can also just look at the values that come in. And so that's how the test bench works. So you need to think of, remember I called it a unit under test? The test bench is over here on its own, except for kind of encapsulates that. And it sends commands to the UUT to do stuff, and then reads the outputs and makes sure that the outputs are what you think they should be. These asserts, they're talked about on page 120 of your book, if you need some more clarity on that. Okay. Thanks. That's test benches.